here I am going to discuss the three type of strains: torsional strain, steric strain, angle strain. So what is torsional strain? So extra energy of the eclipse conformation arising due to the repulsion between bonding electrons of one substituent with the other one. So here this means if you have eclipse conformation, and eclipse means both the group will be on same direction, right? R R, I am writing here R R, backside carbon, okay. Now this is eclipse conformation, and the strain between these two groups are known as torsional strain. Bonding electron, if suppose we have any group here, NH2, CH3, or whatever it is, any group. So here the strain between these two atoms are known as torsional strain. Torsional strain. Okay. Now the next one is steric strain. What is steric strain? Steric strain induced when two atom or group in a molecule are too close to each other, arising due to repulsion between electron cloud. If we have suppose different groups, here we have OH, here again we have any other group. Whatever it is. So here we have these two bulkier group here, right? So the attack of the incoming nucleophile will not take place on these positions because of the steric hindrance. Steric hindrance means lone pair electron cloud interaction. Suppose it also have some electron cloud, this OH will also have its lone pair. So these are type of repulsion which is comes under steric hindrance. So the electron cloud are very important in this hindrance. Sorry, this strain. So we will discuss this in later slides. Now the next one is angle strain. Angle strain is a strain when the molecule is cyclic. Most of the time it is cyclic. So suppose the angle of tetrahedral bond is 109, correct? This is the way. So this angle is 109.5 degree. So CC bond angle is 109.5. If I will keep it in a 10 form, so the angle will become 90, correct? So it forcefully converted to this here, so here the angle is low. Angle is low, so that's why some strain is occurring here. So that is called the angle strain. The molecule is stable with 109.5 degree angle, but it is for restricted to 90 degree in a cyclobutane form. So that is called the angle strain. Next is the example of cyclohexane. We will study the cyclohexane here. So both angle and torsional eclipse interaction strain can be avoided by ring puckering. So what is ring puckering? If I will draw the cyclohexane simply, here this is the cyclohexane, right? Now the angle between them is what? Anyone? the angle is 120, correct? But we need here 109, sorry, not 109, correct? 109, right? 0.5. But here, if it will remain in planar form, it has to become a 120 degree. But because here CC bond rotation is possible, here single bond is there, they will change their conformation. So they can change their conformation. They are changing their conformation into two types. One is chair conformation, the other one is boat. Okay, boat conformation. And here in these two conformation, in chair conformation, the angle is 11111.4, which is better than stable than 120, right? So because this is more stable, so that's why the chair conformation is more stable here. But talking about the boat one, in boat conformation, the angle are stable 11111.4, but here the one thing which is making them unstable, little bit unstable compared to chair, is flagpole interaction. The hydrogens present on these two carbon are interacting to each other. That is called a flagpole interaction. Flagpole interaction. Okay, so the flagpole interaction making board conformation bit less stable compared to the chair conformation, because here you can see that in chair conformation the all the carbon are in tetrahedral form, nearly a tetrahedral form, and they are not eclipsing each other. But in the board conformation, these two carbon are eclipsing to each other. Here I am marking star here. So these two carbon are eclipsing each other if I will look from this or this side, either side. But in the chair conformation, all the carbon atom are staggered to each other, and they are not eclipsing, and nearly tetrahedral angles are there. Tetrahedral bond angle is there. Okay, now let's talk about the energy here. Here the chair conformation are more stable, so that's why it is here. Then it is converted to half chair. What is the structure of half chair? I have discussed only the stable conformation, but the cyclohexane can be retain different type of conformation. Half chair is like half planar and half chair. I will draw better way, in a better way. Like suppose we have here chair, correct? Then chair. Okay, half chair and half planar. So this is called half chair. So in this case, here it is in tetrahedral bond angle, right? But if talking about this carbon, this is also stable. Here is also fine, but here the angle is become 120 again. So it has less stability compared to the chair one. So that's why the energy is very high because of this angle strain here, here, and here. It will become 110 k calorie mole per mole is higher than the chair conformation. Then boat conformation is slightly stable than this one because of structure, but the twist boat is the another form of the cyclohexane. I will show here. Okay, this boat. And what is twist boat? Twist boat is, I will draw here. right. This way. Yeah, this is called बनाई बात नहीं. Yeah, like this. This is twist board. Okay, so in twist board structure, the molecules, the atoms are somewhat staggered to each other, right? Staggered to each other. They are not eclipsing, but the flagpole interaction is still there, and in board form, all the carbons are eclipsing to each other. Correct? Eclipsing to each other. That's why a half board is, sorry, twist board is more stable compared to the board conformation, because of the staggered conformation and tetrahedral angle. Okay, staggered conformation. So this is slightly more stable compared to the board conformation because of staggered conformation. Okay, then the board conformation is 1.4 calorie per mole higher than the twist board one. Now the again it will get converted to twist board, then half chair again, and the this cycle will be completed. This energy profile diagram will be completed by again chair conformation. How they are drawing this way? So suppose we are starting with the chair conformation. With chair, if we will flip or flip this side, it will become half chair. Correct? Half chair. And if I will again, in conformation you can rotate the molecule, right? So we are rotating here. If I will rotate the it into a twist board form, it will give this twist board structure here, and then board, and board will again convert it to twist board, and the energy profile diagram will look like this one. So these all are interconversion of cyclohexane molecule. Okay, now next question is, what among the which among the following is a more stable conformation and why? Anybody? We have to draw both the projection here. In chair conformation, you can see that both are present on axial position. This is called equatorial in this conformation, cyclohexyl conformation. Okay, H equatorial. So this is on axial position. So this is, and these two bromides ion are on equatorial position. You have to draw more stable one. So I will draw the Newman projection here by keeping these two carbon as a axis one. So here we have bromine H, and here methylene, like this group. Okay, and here we have Br, H, and here again CH2. Okay, now talking about this one, Newman projection. Sorry. Okay, so here you can see that these two bromide are Gauss to each other. Gauss interaction is there, and here they are anti. So as I told you earlier, if hydrogen bonding is there, that time Gauss interaction, Gauss staggered form will be stable. But here hydrogen bonding is not present. There is no hydrogen bonding, and these two bromine ion are bulkier atom. So they will repel each other. So the electron cloud will repel each other. Electron cloud around them. Okay. So that's why here we can say this is a steric hindrance. A steric hindrance is present. Due to the steric hindrance, this will become less stable. Okay, and this is the most stable conformation. I hope you understood how to differentiate. Okay, now the next question. Here we have third butyl group on axial position and equatorial position. So as you know, third butyl group is a bulkier group, correct, and all the hydrogens are here. So if we will keep it, if no substituent is present on cyclohexane, so always keep third butyl group on equatorial position, because on equatorial position there is a absence of 1,3 diaxial interaction. Why I am talking about this one? If I will draw the again Gauss interaction, sorry, I will show here 1,3 diaxial interaction is there. How I will explain here. So suppose we have here first carbon, then this third butyl group. Okay, here all are CH, and here we have CH2, correct. I have made mistake in previous example. I forget to mention one thing. Here these are steric hindrance are there between two bromides, but here the another steric hindrance is there. These are Gauss to each other, right? These two groups are Gauss to each other. So it will give the energy 0.9 kcal. Okay, and same here 0.9 kcal per mole. Okay. Huh. So because here two Gauss interaction are there, 1.8 kcal energy is there total here, but the bromine interaction energy is 3 kcal mole inverse, right? So the energy of this molecule is high compared to this one. That's why this one is stable. But we have to consider the Gauss interaction energy. We cannot neglect this one. So they always calculate the energy and then find out the which one is more stable and which one is less stable. Okay. Now in next this question, here we have third butyl group. Again the Gauss interactions are there. Okay. So here Gauss interactions are there, 0.9 kcal, correct? And here again the same thing. 213 diaxial interaction will be there with this one and sorry, with these two one. And in this case, if I will draw this way, correct? And if I will write in a full form, completely open, this will look like this way. third butyl group, right? So here again this interaction is very close, so the energy of this one will be higher compared to the third butyl group present and at equatorial position because of the 1,3 diaxial interaction, 1,3 diaxial interaction, which make molecule more unstable compared to the other one. So this is the most stable structure at equatorial position. Okay, next question. We have to find out the chair and boat conformation stability. We have already discussed. So in chair conformation, here we have H, 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 H. I will draw the Newman projection for these two one. Okay. So if I will draw the Newman projection for this one, I will start from here. Then okay, this is the way to draw the chair conformations Newman projection. How I am drawing this one? By keeping any of the two carbon on a plane. So I am keeping these two star carbon in the same plane, looking from here this center. Okay, so 1, 2 and 3, 4, 5, 6. Okay, so here 5, 6 is this one, 5, 6 and 1, 2 backside one. Okay, and same here we will draw conformation which are eclipse to each other. So I will show this case also. Here we have these two carbon. Okay, I am considering any of the two carbon. So if I will take these two on plane, these two are plane and I am looking from this side. Okay, so 1, 2, 3, 4, 5, 6. Okay, so here 1 and backside is 2. Then because this is eclipsing, they are eclipsing each other, I am imagining from the same side. Five and backside is 6, 1. Okay, so all of you can see that in eclipse conformation they are anti-periplanar to each other, so that's why they are high in energy. So here we can say that this hindrance is called as what we have discussed in previous slide, which strain? Torsional strain. Okay, torsional strain. So in this case there is no strain because it is staggered and more stable. So that's why the energy of this both conformation will higher. So it will become high in energy and low stability. More stable. Okay. I have already discussed the Newman projection. Here it is the example here and the energy calculation. So you can see that eclipse form have a 2.9 K energy for because of the flag pole interaction, while it is not there in staggered form. The next question is classify the following molecule as chiral or achiral. So again we have to think about the symmetry element. We have already discussed the point group. So in point group, when the symmetry is there, plane of symmetry is there, that time the molecule will become achiral, while the absence of plane of symmetry shows that the molecule is chiral. So you can see that if I will pass the plane from here, these are mirror images to each other. So plane of symmetry is present, correct? Plane of symmetry. So that's why this molecule will become what? Achiral. Achiral. Got it? The next one is here. Here now you can see that if I will pass the plane from here, these two sides are not same. This is on wedge bond, this is dash bond. So these are not same, correct? But if I will rotate it by 180 degree on the same axis, it will give us same molecule, which is indistinguishable to each other. But remember one thing, when the plane of symmetry is present, that time the molecule will become achiral. But if the only axis of symmetry is present, C2 axis, that time the molecule will become a chiral. Chirality is there. Only the axis of rotation is present. So the molecule is chiral. The next question is here. Here you can see that we have here 2,3-dichlorobutane, correct? If I will draw it in a Fischer form, I will first convert it into this form, Cl. After rotation it will become Cl. This is the actual molecule. Okay, so you can see that here plane of symmetry is there because this CC bond rotation is possible. CC bond is rotating here. So this is the plane of symmetry present here, and the compound is become meso because the both the Cl groups are on same side. CH3 CH3 Cl Cl H H. So that's why this molecule is again achiral. are chiral because of plane of symmetry. Similarly here, if I will rotate the molecule, this is a free rotation here. This is become like this. So many of you will think like why we are rotating if both are on wedge position, right? Still, if you will think about this molecule, by keeping in this molecule in mind, if you will pass the plane, again this is not the mirror images of each other, because here Cl is downside but here it is upside, correct? It is at downside. Both the both the methyl group are opposite to each other. So here center of inversion is present. We can call center of inversion, but there is at no plane of symmetry. No plane of symmetry. I am rotating this carbon-carbon single bond to make it more easier and understandable. That's why the this bond rotation I am doing here. Okay. So after rotation, this Cl will come on downside, backside, alpha position. So if I will pass plane again, both the chloride are on different position, wedge and dash. So here we can say that plane of symmetry is not present. Instead, the C2 axis is present. C2 axis is present. Axis of symmetry. Okay. So I already explained you, if the axis of symmetry is present, that time the molecule will become chiral. Chiral. Okay. Thank you so much for your kind attention. Here I have ended this NPTEL class week 3 lecture. If you have any doubt, any question regarding this, you can ask me in comment section of YouTube. I am going to upload these slides on YouTube. You can access them from there. And the slides will also available on Drive. Thank you so much for your kind attention.